Another episode of It's Not That Simple is on the air. Today, we're focusing our attention on physics. Our guest is someone who brings science to life with clarity, curiosity, and charm. Helen Czerski is a physicist, oceanographer, and science communicator known for her engaging work exploring the natural world, from the smallest air bubbles in our oceans to the vast systems that govern our climate. A research fellow at University College of London and a regular presenter for the BBC, Helen has a unique talent for connecting complex physics and everyday experiences. Through her writing, documentaries, and public talks, she champions the importance of understanding our planet's systems to make better decisions about our future. We're delighted she's joining us now. Helen, welcome. Great to have you on. We're going to start with a question that we aim to ask all our guests, which is explain why a particular topic is not that simple. So to break down physics, how would you do it?
Well, the first thing is that physics is all about patterns. And so you say it's not that simple, but actually there is a simplicity to it, which is that we know the rules of the physical world. And what we find in the real world around us is that they're all laid on top of each other. So the patterns themselves can be quite simple. And the place where the world becomes interesting is when you've got multiple competing patterns. So, for example, in physics, you might have a competition between gravity and electromagnetism, and that can generate interesting things. And the reason our world is such an interesting place is that each pattern is quite straightforward, but we live in a world where they're all competing with each other. And if you go a bit bigger or a bit smaller, the outcome of that competition is different. And so the thing that I think people's conception is that physics is somehow very, very complicated and very, very far away. And actually, that's not true, because we all live in the physical world and we all have physical intuition. And it is the case that we can see the patterns of physics around us. So I think it is more simple than most people think. So I would challenge that it's not that simple, but it becomes complex when these different patterns are all overlaid on top of each other. So it's a bit of both, really.
Okay, well, we'll get into both then. And when you break down the work that you do, tell us, giving practical examples of how your work across the different areas of study and practice, how they help us understand our planet better, how they help us understand our environment better.
Well, fundamentally, I'm interested in the physics of the everyday world, which is the world around us. And so some of that is our own lives, and some of that is just the planet, which is our life support system. And so physics basically sets the ground rules for both of those life support systems. And when it comes to the planet, you've got all this mass moving around, you've got energy flowing from one thing to another. And the way that the mass and energy interact is what creates the world around us. And I've got particular interest in the ocean, for example. And ocean physics is the physics of liquids, largely. The ocean is mostly liquid. And you can look at the big forces that are pushing the ocean around, that are pulling it, that are making it function like an engine. And then you can see the direct consequences of that in our everyday lives and in our history and our culture. So the consequences of the physical engine are written through the way our civilization is built. And I think it's really interesting, that if you learn a physical pattern, it's not just, you don't just say, oh, well, that's very nice and it's very interesting, and then you stop. You then say, oh, this is this physical pattern, and it explains all of these other things. It explains why something happens like this and not like that. It explains why this bit of history turned out in a particular way. And so everything is linked. I mean, that's why I think physics should be interesting. Yes, there's a curiosity about the sort of the very pure side of it, that these things can happen, but actually the much more interesting bit is the way they do happen in the real world and the consequences that they have.
Okay, so what are some of those phenomena? What are some of those patterns? Which are some of those situations that you study, that you use when you're exemplifying to whether it's students, whether it's stakeholders, of why they should care about the depth of work that you do?
So, well, let me give us a specific simple example that perhaps will set some context. And this is just a random thing. This sort of thing's happening all the time. Now, I don't know if you've ever tried telling the difference between a raw egg and a boiled egg while their shells are still on. So you can boil one, you don't boil the other, and then they're both cold and they're sitting in front of you. How do you tell the difference? And the answer is that you spin them on their sides, so they're spinning on the table, and then you just put a finger on top of the shell and take it away. And if you do that with both eggs, you will be able to tell the difference between the one that is raw and the one that is boiled. And the reason is that the solid egg is solid. And so when you touch your finger on top, you stop the whole egg. But when you put your finger on top of the liquid one, you only stop the shell. And so if you take it away quite quickly, inside the liquid is still spinning. And so and there's a principle here, which is conservation of angular momentum. So once something starts spinning, it will keep spinning unless something stops it. So actually, once you take your finger away, the liquid egg will start spinning again. So most people, once they have tried it, they know intuitively without actually knowing the physics which one is true. So there's a principle there, which is the conservation of angular momentum. And the same principle, exactly the same physics as the egg, that's what keeps the Hubble Space Telescope, one of our most exciting and successful outer space telescopes, that's what keeps it pointing in the right direction. Because we use the same principle in space with a gyroscope, so that inside the Hubble Space Telescope, there is something that is spinning. It's not an egg, but it's a solid object that's spinning, and it will keep spinning with the same orientation and at the same speed, even if the spacecraft moves around it. So the spacecraft actually knows where it is because of this gyroscope, because of this principle of angular momentum, which is exactly the same as the egg. And then you can carry on. There's lots of other examples. You can build up, for example, the Earth itself is spinning, so lots of things on the Earth and in the ocean are spinning, and this conservation of angular momentum continues to be important in all of those cases. So it's that kind of thing. Once you've seen a pattern in one place, then you keep seeing that pattern in other places. And then my type of physics, I study the ocean surface and breaking waves and bubbles and how gases go in and out of the ocean. But really, it's an application of the same rules of physics that we see around us. And the point here isn't that it isn't clever, it's that it is accessible and that all of us are able to think about these things. And actually the cleverness comes in the ingenuity of all the different ways you can use it, because physics is like a toolbox. And once you understand the tools, you understand about angular momentum and you understand about gravity and you understand about surface tension, a few of these tools, suddenly you can not just explain the world around you, but you can interact with it. You can do clever things. You have agency. And that's the point I think that I would like to get to, that people feel that they understand enough of the world around them to ask good questions, but also to really use that toolbox to make the world a better place in whatever they're trying to do.
It's interesting because as much knowledge that we have about everything these days with the bombardment of information that we kind of have through digital and social media, I feel that many times our knowledge of abstract and physical topics, such as technology, keeps growing, but the knowledge of the planet and the world around us actually becomes somehow limited. What do you find with young people mostly of what they know regarding how the planet works, and talking about oceans and the importance of the oceans to our ecosystem?
I think things are changing quite quickly, actually. So 10 years ago, it was certainly the case that the only thing most students knew about the ocean was that it was wet and it had fish in it.
Okay.
And that, there's basically culturally been two choices of how to look at the ocean. There's the one where you say it's a void, it's just empty, it's just sort of nothing space. And then there's the one where you say it's a monster, that it's this nasty thing that's trying to attack humans and you've got to fight against it. And those have been the two options. And of course, that's a very poor view of the ocean. It's very thin. There's not much there. And of course, what we've done to our natural environment is a reflection of thinking about the ocean like that, as either a space to put things into or just something to ignore. But what I do see now is that younger people they're making the connections. They're hearing about climate change. They're looking at the world around them. And fundamentally, when you're growing up, you're looking for these frameworks, right? You're looking for these big explaining principles, this kind of skeleton that you can carry through life that's going to tell you, here's the basic shape of things. And then as you go through life, you can keep adding in new bits of information to make it richer and more informative. And so therefore, now I think when young people are forming a view of the world, it's much more likely, it's not 100%, but it's much more likely to include the natural world with some respect, not as something to exploit or to plunder, but with the idea that it's doing something. Mm-hmm. And one of the things it's doing is keeping us alive. And so if nothing else, we're self-interested, right? We want to stay alive. And so we need to know about what that, we need to respect the natural world and look at what it's doing. So I do think that's changing, but there's still what tends to get communicated to young people now is the problems. And that's the risk that people say, oh, well, this is happening and it's terrible and all the fish in the ocean are dying, or all the, there's this list of problems. And the problem with that is that then what do? Right? Yeah. You just, there's a problem. And now I'm stuck. Now I feel bad. Yeah. And I don't know what to do. But if you have painted the picture of what the planet is and how the system works, then when someone says there's a problem, you're like, oh, well, would this help? Would that help? You've got some agency, you can do something about it. And so I think young people now are, the risk is that we only tell them about the problems because, we as adults say, oh, well, that's very serious. We want to shake you by the shoulders and say, do you understand how serious this is? Yeah. But before that's going to work, they have to understand what nature is and how the planet works. And they have to care about it and see that mostly it does still work. It's not a complete disaster yet. Yeah. I mean, things are pretty bad, but they're not lost. And then once they see a framework and that you identify a problem, then they start thinking of solutions. And that's what we need, is to kind of make those steps through. So I think only talking about environmental problems, it just doesn't work. It just makes people feel helpless and awful. But as soon as you give them a framework, as soon as you say, just think about the whole thing like this, and then identify the place where the problem is, they're off. They're inventing all kinds of interesting things and they're doing a good job.
Well, let's get into how some of these processes work then. And I wanted to ask you about, when you talk about the ocean, whether it's turbulence or wave breaking, how do they connect to big picture climate systems?
So when it comes to wave breaking, this is obviously at the boundary between the atmosphere and the ocean. So the atmosphere is very, very big. The ocean is very, very big. And there's this boundary between them, this thin layer, the ocean surface, which is in control effectively of everything that goes from one to the other. And so there are three things really that cross the ocean surface. One of them is energy. So when the wind pushes on a wave, it pushes the wave up and the wave travels. Eventually the wave breaks and that forms turbulence in the ocean. And then you've got turbulent energy in the ocean. So you've taken energy from the wind and you've moved it into the ocean. And that's quite important for the way the planet works. The next thing you can move is momentum. So that's just the push. The wind has some momentum and by a similar process, it pushes on the surface, it pushes currents along. And then you've shifted momentum from the atmosphere into the ocean. But the third one, which is where I work, is the other thing you can move across that boundary is matter, stuff. And it can go in both directions. And mostly that's in gas form. So we're talking about gases like carbon dioxide and oxygen that if there's more in the ocean than in the atmosphere, they'll go down into the ocean. And if there's more in the ocean than in the atmosphere, they'll go up the other way. And so these gases are really important for how our planetary system works, and especially carbon dioxide, because the ocean takes up carbon dioxide because we're putting extra carbon dioxide into the atmosphere through burning fossil fuels and land use and a few other things. And that means there's a high concentration in the ocean, in the atmosphere, and a lower concentration in the ocean. So carbon dioxide will tend to go downwards. But if you have a big storm, you're mixing everything up, there's loads of turbulence, that downward speed is going to go much faster. Gotcha. So basically, the ocean can take an enormous deep breath in a storm. And so that's what tends to happen closer to the poles. So in the North Atlantic, for example, the ocean is breathing in carbon dioxide. And at the tropics, it's breathing out carbon dioxide. So there's a balance of both. And what we're doing is, putting more carbon dioxide in the air, so more is going in. And the thing that is really useful about that for us is that it takes it out of the atmosphere, and that's where it would be contributing to global warming. So if it goes in the ocean, then we've saved ourselves that problem. We might have created a couple of others, like ocean acidification, but it means there's less heating than there would otherwise be. And so these tiny processes, breaking waves and bubbles at the ocean surface doesn't sound very important. But if you want to add up how much breathing is going on around the planet all the time, and especially if you want to ask, so the ocean is doing us this massive favor. It's taking up all this extra carbon dioxide. And the big question is, will it continue to do that in the future? Because if it doesn't, we've got a real problem.
Yeah.
And if you want to answer that, then you need to know what is it that influences whether the ocean is breathing in or breathing out? And what is it that influences how fast it's breathing in or out? And so that's where you get to the physics of the ocean boundary. And so this is not just about being able to understand the planet as it works now. It's also about being able to predict the future and to be ready for that future, whatever it happens to be.
One more question about oceans, because you do a lot of work with bubbles. What's some surprising features of bubbles that reveal how the oceans are functioning?
There are a lot. When it comes to how the ocean is functioning, I guess one of the sort of straightforward one in a way is that bubbles make water squishy. So water is really hard to compress. Like if you have just pure water and you try squashing it, it really doesn't get very much smaller. Even right in the deepest parts of the ocean, where you've got an enormous weight of water on top of it, it's only squashed by 1 or 2%. So water is not very squashy. But if you put gas bubbles in it, water becomes much squishier and you can compress it. And that means that sound travels differently through the water. And so, also if you're a fish and you've got a gas bubble inside you, which many fish do in their swim bladder, it changes how the sound travels through the fish.
Okay.
So in this case, it's actually not so much about global change, but it is about, that change in how the sound moves through the fish because of this bubble in the middle of it, that has made it much easier for us to find fish. So now it used to be that fishermen would go out to sea and they had past knowledge and they knew what the weather was and they had experience to go on and they would just hope to find some fish. Now we have sonar systems, so systems that send sound downwards into the ocean. And if you get a fish that's got this gas bubble inside of it, which is most of them, it reflects it sends it back up so you can see the fish in the ocean. And that was never possible before. And so that has contributed to overfishing and the state of the biodiversity in the ocean, just because of the physics of the bubbles, basically, inside the fish that let you see where the fish are. It's like a sneak peek into the ocean. So, so there's that kind of direct application of bubbles. And then the stuff I'm doing is just telling us, enabling us to predict the future better and predict the future of the climate better.
Okay. All right. So kind of zooming out into the overall work that you do. Obviously, you do a lot of it across cutting edge research, then a lot of communication around public science as well. How do you balance all of this out? How do you keep the complexity of a lot of the elements that you're studying and communicate them in a simple way to engage the public?
It is like doing more than one job, honestly. But the thing that is similar, though, and I think this has got lost a bit, is that modern science has become very much about the details. You get specialists who zoom down and down and down, and they know this tiny, tiny detail, and it's really important. But it's kind of it's the edge of the edge of the edge. And it's really small, and it's very easy in modern science to just find the next little small thing we don't know. But that's because we've got really good technology that lets us look at those really small things. And the habit that modern science doesn't have quite as much is the habit of standing back and just looking at the whole picture. Because you don't get grant money for that, right? No universities are paying researchers to just think about what is the really big picture here. And how do all these pieces fit together? Now we've learned more in lots of these very small areas. How does that change our whole conception of the planet? And so, but that's what my work as a communicator is doing, right? That job of communication is about, it's not just about sharing facts, it's about sharing perspectives. That if you know all these things about the world, it gives you a certain perspective on how the world works. And so I think that's where the overlap comes, that in science as a whole, people don't have time often to actually really think about what it all means in a really big way. But as a communicator, that's my job. That's how that's the sort of the service I'm offering to the public, is that if you look at it like this, suddenly it all makes sense. And so there is overlap in those two jobs. And some of it is in being able to be really rigorous about the science, be really rigorous about the question you're asking and what information you need to answer it. And that's an essential skill, especially in a world where there's lots of misinformation and people just write things on the internet and then everyone else assumes they're true, right? Yeah. You have to really know where to go to get information, to really check, did that actually happen? Did it happen on that day, in that place? Specifically, is that a real thing? So you need that skill, but then there's also this just framing argument that, if you can make the framing argument, you can actually change the direction of science. And that's what I'm doing as a communicator. So I think they do fit together. It sounds a bit weird, but they're both about prioritizing ideas and then knowing how to look at those ideas in a way that will take you to the next step, that lets you ask the right question.
Okay, so if I were going to ask you to maybe highlight 2 or 3 key aspects of the planet, of our world, that you've learned the most about, that you can share with our public, what would those be? What are the most important learnings of your work so far regarding the planet, regarding the ocean, regarding the atmosphere, whatever they may be related to physics, that we should take?
I think the biggest lesson of all of it is how incredibly interconnected these systems are. So it's never the case that somewhere in nature something just happens here and it doesn't affect anything else. So, for example, I learned the other day that the whales go on very long migrations, and they migrate from the Arctic often down to the tropics. And what they're doing in the Arctic is feeding, and what they're doing in the tropics is breeding. And so whales don't, when they're breeding, they're not feeding, but they do still produce urine because their metabolism is still going. And that urine deposits nitrogen on tropical islands. So a lot of these whales go to places like Hawaii, they hide in the shallows, they have their young there. And those places are not rich in nutrients, but the whales themselves are delivering a significant amount of nutrients. So they are fertilizing their local environment. And that's just with one long migration, that's one species, and they are making a significant difference. So one of the things that's not appreciated is that when we killed whales, when industrial whaling took a lot of whales out of the ocean, it's not just that you remove a big whale and then it stops eating whatever it was eating. These whales are actually moving nutrients around. They're moving them sideways, they're moving them up and down. And so you've taken away one of the mechanisms that made the rest of the system work. And really, I think that's the type of big, and that's an easy example because it's an animal and there's some that are, a bit more physics-based. But fundamentally, that's the biggest message of our time, actually, is that all of these processes, the physics and the biology and the chemistry, are all interconnected. And if you take away one part, as we have done through, overfishing and adding pollutants to the ocean and all that kind of thing, if you remove one part, you kind of break not just a chain, but a web of interactions. And so I think that those are the lessons that are really being reinforced in modern science in all kinds of areas, in physics and chemistry and biology, especially in the ocean, that this is interconnected. It's never just about that one place. And what's happening in that one place is always affecting something that's happening elsewhere. So that's one, it's kind of a slightly nebulous example. It sounds a bit vague, but it's really, it matters. Just for another example, the biological ones are easier. So sharks feed out in the open ocean and then they come to coral reefs to feed. And when they feed, they also they poo, right? They produce feces, and that fertilizes the reef in these places where there's no nutrients. There's no land that's producing lots of nutrients. So the sharks are bringing nutrients to the land. And this kind of thing is happening all the time. And in the physics world, it's often more to do with ice, for example. So if you melt the ice over the Arctic or melt more of it, we know that changes, it will change the big ocean currents. It changes how water is heated up and cooled down, and it changes how the overturning engine will work and exactly where those currents will be. And so if you affect ice in the North Pole, you also affect our weather here in Northern Europe. And so I think those connections are the things that it's not a single physical principle. What we're learning about is how these things work together to create the world that we take for granted.
I think you've really summarized a lot of the work you do very well, and the interconnected nature of all these forces. And when it comes to science, I think it's really important for, I think, especially the young generations, to understand the impact as well of a lot of the behavior that the human beings are having on the planet. Last question before our little quick fire section that I had for you is, when you say that a lot of the work you do helps us have a picture of what the planet's like, what is the planet like at the moment in 2025, Helen? And when you say you also can help predict the future, what kind of future do you predict at the moment?
The planet is not in a great state, but it's not dead yet. And that bit is really important. Most of the ocean engine is still functioning. Most of the atmospheric engine is still functioning as it was. It's just changed in some ways that make life harder for us humans and for other species on the planet. So when it comes to a summary of how the planet's doing, there's more energy in the system. It's shifting things. It's shifting currents and storms that we took for granted, and maybe they appear earlier or they appear differently. So the patterns of the engine are changing. And of course, we've built a civilization that depends on them being as they are. And the species in the ocean and on land have built lives based on things being as they are. So I think that we have a massive problem. But the good thing is we also have the means to fix it. And it's really important that we understand that we do not have to wait for some amazing new technology to do this. We don't have to wait in order to make these changes. That we know now what to do, and we just have to get on with doing it. And what's holding us back is mostly social factors and acceptance, and the keenness of people who do well out of the current system, should we say, to keep benefiting from it, whether or not that's good for the rest of us. But when it comes to the future, it looks to, in my specific field of how carbon dioxide is taken up by the ocean, it looks like the ocean will do less of that in the future. It will not do that favor as much. And so more of the carbon dioxide that we generate by burning is going to stay in the atmosphere, and that will accelerate the warming of the planet. And so we can see that sea level rise is going to become significant because warmer water takes up more space. And if you melt ice, you're adding even more water. So these are really serious problems. And I don't want to underplay this, because I think that there is this kind of assumption that humans have that, well, it'll sort of be all right. COVID came and went. Yeah. How bad can it get? Yeah. Actually, it can get really bad. And the sooner we really take this seriously, the better it will be. But the good thing is that I see people all around me who are making these changes. It's one of the interesting things that when you look at global surveys of what people think about environmental harm and climate change, the vast majority of people in every country want action on climate change. They want this to get better. They don't want to live in a world that is broken, basically. And they're prepared to do things to make that happen. But there's this idea, because most people think that, but most people are quiet. And so it's easy to think that the only people who care are these two people, either climate deniers or sort of hardcore environmentalists, and that nothing else is in the middle. Actually, most people are in the middle, and most people want action and are prepared to do it. And there's so many community groups and local grassroots, sort of action that is happening. People are not waiting for governments. They're just getting on with installing solar panels, insulating schools. They're just doing it. And, so I think this is a really serious problem, but actually we are already on the way to doing good things about it. And we're not alone. And those things are really important. So we need to do more. We need to do it faster. And we know what we need to do. We need to stop burning fossil fuels. There just can't be a debate about that.
No doubt.
But we know how to do it for almost everything, possibly with the exception of air travel. We know exactly how to do it. And we just have to say, we want this. And actually, people sometimes say, well, it might be, maybe it's expensive, or they think it's going to be expensive. Quite a lot of the time, it is cheaper in the long run anyway. And even beyond that, the costs of not taking action are phenomenally high. And that is never, that rarely gets mentioned in these conversations.
Right.
Like maybe, it might cost you 10% more to insulate your house. But the cost of climate change in 50 years' time, if we don't do this, is astronomical, like absolutely breaking the economic system. So it's, there's no logical reason not to do this as quickly as possible. And we can do it. And it feels now like there is movement in that direction. And that's partly because people want to connect to the world. They see these connections and they're like, okay, I like trees. That basic thing of I like nature, I like trees. I want nature, I like being in nature. Let's do what we can to protect it.
Yeah. Let's wrap up our conversation with 4 quick-fire questions that we ask all our guests. So in one sentence, not too long sentence, in one sentence, I'd like you to answer these. So the first one is, what is one personality trait that a good leader could really benefit from having, and why?
Humility. Being like a teacher with humility, which is the way the indigenous populations, their leaders are all teachers, and their teachers all have humility.
Yeah, and as we know, a lot of leaders around the world that are lacking that right now. What is the biggest challenge humanity faces today?
I think it is believing or being seduced by the model of capitalism that we have now, and being seduced by the idea that we can be good, that the only route out of this is to be good capitalists. And I think that we have to challenge our assumptions about society more than that.
If you could change one thing in the world by magic right now, what would that be?
I would. That's a good question. From a practical point of view, obviously, what I would do is get rid of poverty and health inequality overnight without environmental damage. That would be one of the. If you could do those two things at the same time, and I think we could, you offer the world an enormous route forward to us having a better, fairer, and healthier society.
And what is the most, we've talked about your learnings, but what is the most important learning of your life and career? If you could sum up one of them that is crucial, that is the most impactful.
That it's about the humans around you, right? The best thing about being human is being human and other people, and it's the people that matter. So we have to remember, there's a quote in the Einstein-Russell Manifesto, which was written about in support of nuclear disarmament in 1955, and it's got this sentence in it which says, remember your humanity and forget the rest.
I think that's a fantastic way to end this conversation, Helen. Thank you so much for being part of the show and helping us see physics from a 360-degree perspective, and understanding how, in the work that you do, it's clear to understand how everything is truly connected. So thank you. Continue your great work when it comes to the physics side of it, but when it comes to the communication side of it as well, because as we know, that is so important that our communities know about facts and how those facts can shape valid and credible opinions to find solutions to the problems we have. So thank you.
Thank you very much for having me on.
That was Helen Czerski here on It's Not That Simple as we delve deeper into physics. And it was fantastic to get an opportunity to learn more about not just the science of physics, but truly how it affects all of us and our living environment on a day-to-day basis. See you soon. It's been another fantastic episode of It's Not That Simple.